Hello everyone, my name is Lixiang from IBM Research. Today I want to present our study on localized NVMe storage virtualization for public clouds virtual machines. While the primary goal for this work is to support the enablement of localized NVMe storage on IBM Cloud, we do hope that the study can provide general guidance for supporting localized NVMe in public cloud virtualized environment. Here is a summary of what to expect in this presentation. After quickly go through the motivation, we will discuss the three virtualization options. Then we will present our performance assessment results so that we can compare these three options. Multi-VM tests were also conducted, which will be discussed. Security considerations are particularly important in a public cloud setup, so we will discuss that before the conclusion. So why do we need localized NVMe storage? In fact, public cloud providers are quickly adopting NVMe to meet performance demands. Applications include high throughput databases, GPU-based training, and more traditional high-performance computing applications. Public cloud providers support local NVMe in different ways. IBM and AWS have support for bare metal nodes for a while. For cloud virtual machines, AWS, Microsoft, and Google have been providing local NVMe solutions, and IBM recently added the support. This study was part of the effort to provide support for cloud virtual machines. There exist quite a few options for NVMe virtualization, but we ended up focusing on three of them. The first one is device pass-through. So the whole NVMe drive is passed through to the virtual machine, and the guest can do whatever it wants with the device. Apparently, the host loses most control, and the details of the hardware is completely exposed to the end user. The second option is for I/O block. With this option, the VirIO block emulates a virtual block device interface using either image files or NVMe namespace. The nice thing about using NVMe namespace as the backing mechanism is that the host can leverage the secure wipe function provided by NVMe namespace and render the data completely invalid by dropping the encryption key. The third option, SPDK vhost, is considered a good compromise. On one hand, it provides great performance, almost as good as device pass-through. On the other, it still provides an abstraction layer, which allows the host to impose additional control, such as security measures and quality of service functions. Here are some other options we didn't consider. We skipped pair virtualization because of the security risks. Mediated device pass-through is similar to SPDK vhost, but the technology is not mature enough. Now let's dig a little deeper on each option. First is the PCIe device pass-through. Essentially, an NVMe is just another PCIe device. PCIe device pass-through is a mature technology. It is supported by most modern CPU and motherboard. Virtual machine gains full and exclusive control of the NVMe device. So that's why the biggest advantage is the near bare metal performance, best peak throughput, lowest latency. But it also comes with a lot of limitations. The device, once passed through, cannot be shared by multiple VMs. Live migration is not possible. Hardware specifications are fully exposed to the end user, and there's no quality of service control. Let's talk about the VirtIO device backed by NVMe namespace. First of all, an NVMe storage device can be divided into one or more namespaces. NVMe namespaces is an inherent, the built-in feature of the NVMe specification. So every NVMe device has to implement this feature one way or another. Namespace management is carried out by the NVMe controller on the hardware level. The mapping between NVMe controllers and namespaces is flexible, but in this study we only care about the situation where one controller managing multiple namespaces. Now let's go back to how QEMU implements the VirtIO devices. It is actually quite similar for VirtIO to use image-based storage backing or a NVMe namespace as the backing mechanism. In both cases, QEMU VirtIO provides quality of service and caching. The sharing of the device is very flexible. It can be shared by multiple VMs. Hardware encryption is also available. The biggest limitation or disadvantage of VirtIO device is because of the emulation overhead. The throughput is generally lower and higher latency as well. So here is a table summarizing the pros and cons of different NVMe virtualization options. There are several considerations such as sharing, performance, scaling, live migration, CPU consumption, security, quality of service, and technology maturity. And we can see that there's no clear winner here. It's just that how the solution can fit into the needs of a cloud environment. So eventually, we focused on the namespace as a block for our implementation of local NVMe storage on IBM Cloud. But for other cloud setups, the choice may be different. So now let's move on to the performance study. We focused on using the workload emulator FIO. It's widely used, especially for benchmarking I/O performance. Tests are carried out for various combinations of parallel threads, queue depths, and read-write ratio. This approach can give a very good high-level overview of performance trends. Beyond that, we also try some real workloads, including AlexNet training or ImageNet 1K using PyTorch, and also RocksDB benchmark
This is the benchmark which comes from the RocksDB software package itself. For performance metrics, we focus on system-level statistics, such as CPU occupancy interrupts, context switches, and I/O operation counts, etc. So here is the performance test configurations. The server nodes we use is manufactured by Supermicro. It has Xeon Go 16148 with 28 cores and 1 terabyte memory. It has 8 V100 GPUs, runs Ubuntu 18.04 and QEMU 4.2.0. The FIO version we use is 3.17. The NVMe hardware we use is Samsung 1725. It can provide up to 6.2 gigabytes sequential read and 2.6 gigabyte per second sequential write. And the NVMe controller can manage up to 32 namespaces. It also supports instant secure erase, we mentioned in previous slides, that can be used for almost instant data wipe after the NVMe is released from the guest. Samsung 1733 is used in some cases, but with similar results. Now let's take a look at some numbers. Here is a comparison between device path-through and bare metal. As you can see in the figures on the right, we focus on 4K random read scaling over the number of jobs as well as the queue depths. As you can see, the performance between the two is almost the same. There's slight penalty for device path-through for longer queues, but such situations are quite rare in practice. Host CPU load is basically the same as number of FIO jobs, which is not surprising at all. There is no CPU load beyond the number of FIO jobs. So the summary is device path-through is almost the same as bare metal. So one finding of our study is that using deeper queues is usually beneficial. Basically, deeper queues offer better concurrency without much trade-off, and we can see that because queues are handled by hardware and they're completely asynchronous, CPU load is not affected as the queue grows deeper. So if the application can be modified to use deeper queues, it's a good strategy for getting better performance from the local NVMe. So we already know that device path-through is almost as good as bare metal, but can we improve beyond that? Actually, we found a way. It's just we need to run SPDK inside an VM on top of device path-through. In this case, the SPDK has no knowledge of being run inside an VM, and it just keeps pulling using its pulling mechanism. So actually that completely, or should I say, eliminates most of the interrupts. And as a result, the virtualization overheads are greatly reduced. We find that the performance is even better than bare metal. It scales better than bare metal when the deeper queues are used, although at a price of 2 CPU cores, regardless of the number of FIO jobs. So the limitation is that the application must support SPDK directly. So if you want to use SPDK, you have to change your source code. And the cloud user, the end user, must set up SPDK inside their VM on their own. Now let's talk about the namespace-based VirtIO block option. So performance-wise, namespace-based or file-based VirtIO devices are quite similar. Both have significant more overhead in the software stack. Bandwidth is far from peak NVMe capability. Aggressive optimization would be required deep inside the software stack if we want to improve upon this. With caching, this option provides reasonable performance and even sometimes a slight advantage over device path-through for very shallow queues, where that is queue depth less than 8, or even synchronous I/O. About 2 cores worth of CPU load is observed, mostly due to software caching. SPDK vhost target is a more recent option for NVMe virtualization. It provides 3 interfaces, NVMe, SCSI, and block. So with some performance study, we found that currently, as the time of the writing of the paper, vhost user SCSI is the best option among the 3 overall. But there is really no big difference between the 3. Looking at the performance of SPDK vhost, we can see that it offers a attractive compromise between device path-through and namespace. It has vhost target and VirtIO block has similar CPU load, but vhost has better scaling and higher bandwidth than the VirtIO block. Because VirtIO library is involved, quality of service is supported. However, it's not yet adopted by any public cloud providers because there's no clear advantage of VirtIO block for shorter queues, and it requires dedicated huge page memory on host for DMA. We also did a performance study using a RocksDB benchmark test. We all know RocksDB. We are using the read while merging, which is one of the standard benchmarks included in the software, which mostly stress the random read performance. It's tested with a 3 terabyte randomly generated database. And the bandwidth we observe, as you can see in the figures, are consistent with multi-threaded random 4K read performance measured by FIO. CPU load is dominated by database operations, therefore no significant difference between all the sharing mechanisms. Data privacy and security are an important factor for enterprise tenants. All data must be fully unreadable after the NVMe device is released by the tenant. Data erasing protocol designed for spinning disk are not sufficient for NVMe. So instead, we can simply discard NVMe's namespace encryption key to do an instant wipe. Other approaches being considered: Lux, its software solution is slow. NVMe self-encryption drive, SED. So there are some recent development in the specification which enables more robust security mechanisms. Yeah. So in summary, device path-through provides near bare metal performance, but with obvious limitations on elastic scalability. Device path-through plus SPDK can further improve performance, but it's not trivial to adopt this approach. VirtIO block provides reasonable performance for shorter queues and flexible management mechanisms, but performance for multi-threaded I/O is lacking due to software overheads. SPDK vhost is an attractive middle ground between device pass-through and VirtIO block, providing benefit of VirtIO block but with much better performance. Although technology maturity is a concern. There are various security considerations in each option, but namespace serves as a foundation of most solutions. Here are some ongoing and future tasks regarding NVMe virtualization. For example, multi-VM scalability, SRIOV, further study of performance and characteristics using real workloads, explore security and encryption options, further study of SPDK and vhost target, and we will continue to collaborate with Red Hat on furthering our understanding of NVMe virtualization options. And that concludes my presentation. Thank you very much.